your moment of inertia is small, that would correspond to, with linear motion, a very, very small mass. If something is really small, is it easier to move around? Yeah, it does want to move around. That's not the best way of saying it, but it kind of captures what we're going to. It does want to move. So we would say over here, sorry, I should have written this initially. High inertia means it doesn't want to rotate. It's sort of like, I don't really want to spin around a little bit, okay? But if it's got a low inertia, that's like low mass. It's like, yeah, let's go. Woo, 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 woo. Let's spin around. So it does want to rotate. Mass is pretty much based on how tightly the atoms are jam-packed in there together, okay? So, mass is, of an object is based on, it's based on the volume and it's based on the density, okay? The moment of inertia is based on two things, okay? So it's, in our situation, we have something kind of spinning on this pivot stick here, all right? It is based on the mass, and it is based on the location of that mass. And specifically, it's based on the distance from where that mass is, where the weight is, in relationship to the pivot point. And that distance is called R. So what we're discovering here and sort of experimenting with is, okay, if R is really small, how does that affect the moment of inertia? If R is really large, how does that affect the moment of inertia? Okay? That's what these guys are designed to show. Now, if I were to do this the best possible way, in the most proper way, Jesus, come up here. This is what I would do. Unfortunately, this best possible way doesn't, it's really subjective and it's really hard to do, okay? So technically, if I could really do it, can you all notice I have one situation where these are both the same rotator stick, okay? And they both have 4 2x4 Lego bricks stacked. This one, the R value is really small because it's really close to the pivot point. In this one, the R value is really large. A lot of the mass is all distributed towards the end, okay? So these two sticks would have different moment of inertia, okay? They would have different moments of inertia each. This one would have a moment of inertia of some number, and this would have another number. The question is, which one, what would be those numbers? Which one really doesn't want to rotate? Now the problem with this is that if he's going to tap it, I would say, Jesus, provide the same force to this one to get it to accelerate, or actually, wait, it's a force that causes it to rotate. What's a rotational force? We don't call it a rotational force. A torque. I would say, Jesus, apply the same torque to this rotator stick that you're going to apply to this one. That's really hard, okay? Because you're going to sort of naturally tap one of them a little bit harder than the other to try to get the same effect. But we'll see if we can get it to do. What we are going to do is we're going to see, assuming everything's equal, assuming that there was the same amount of friction and he pushes them both the same amount, this is what I'd like to do. Tap the hard one. Tap that one right there. Once again, this is why we don't do this. Okay, Mission, you're going to have to go dive underneath there. Okay. Let's go, Mission, come on. Tape's rolling, glass is digging. Come on in.
Sorry to interrupt.
Sure, what's up?
Can I interrupt this real quick?
Sure, go for it. All right, let's try to, okay, apply torque. There we go. Now apply the same torque to close one. Yeah. See, that's the problem. They both landed at the same point. See that? That's really not very helpful. Okay, you can take a seat. So that's why, because we've got so much stuff and the friction effects are the same. But this is what we can say. I can wiggle this one a little bit, which is basically like applying a torque. And I can wiggle this one the same amount and not so much. Wiggle this one a little bit, wiggle that one. This one. Finally gets going. Which one of these doesn't want to rotate? This one. Can we all agree on that one?
Yes.
Great. Now, Brooke, observe. Do a little bit of wiggle. Woohoo! A little bit of wiggle. Finally gets there. Right? A little wiggle. Wiggle. Which one of these doesn't want to rotate? The one where it's far away. Okay? So, all of that to say this. If I can finally get it. All right? With the moment of inertia. If the radius is really high, if you have a really high radius, if the mass is distributed far away from the pivot point, then your moment of inertia is really high. That's the first point that I wanted to show. Okay? Obviously, if r was really small, then moment of inertia is really small. The next thing that I was going to show is this situation. Still the same rotator stick, but what do you notice about this one over here? There's a lot more mass on there, right? Okay? So, all right, it's pretty much the same when it comes to pushing something or whatever, okay? Which one do you think of these two is not going to want to rotate?
Well, you're right.
The one with more mass. Why not? I said, which one do you think is not going to want to rotate? Okay, yeah, because that's more inertia. That's kind of the question. Yeah, and what it boils down to is all these guys, those little particles, those molecules there, they don't want to move. They don't want to move unless they have to. If I'm going to get those suckers to move at the same rate that I'm going to get this thing to move, I'm going to have to apply a lot more force, a lot more torque. Okay? So let's see if I can do this really quickly. All right, I'll do a little bit of a wobble here. Whoop. There we go, a little bit of torque here. No, thank you. Okay, do a little bit of a torque here. Whoa, woohoo! They're going around, no problem. Okay, accelerating. Oh, that was. There we go. Got it. Yeah. Now, this is what you feel. Once you get it going, okay? See if I can get it going. All right. This one over here on the left, it wants to keep going because an object in motion tends to stay in motion, okay? And you got a whole lot of objects that are in motion right there. They really want to stay together. These guys over here, they want to stay together as well, but they don't have as much something we'll learn about later called angular momentum. All right, there's the friction is really affecting this one. This one's sort of like, you know, this one's like 100-pound weakling. You know, and this one's like the, you know, like the 250-pound strongman. You know, I mean, this one once it gets going, you know, there's not much stopping it. All right, you know, a little, you know, 8th grader run into you, he'll bounce back. But you know, this is the unstoppable force here. Okay, once it gets going, it's really going. Sort of like a real car versus a toy car. Okay, a little toy car, you can get that thing to accelerate no problem. You can also get it to stop no problem. Okay, a big car has it's difficult to get it going, but once it's going, it requires a lot of force to stop it. Anybody ever tried to push a car before?
Yeah.
Okay. All right. What's really interesting is once you actually get the car going, and you've got to stop it. Well, unless somebody's in there with the brake, then you're going to be in trouble because you have to apply just as much force to stop it. We'll talk about that more when we get to chapters 9 and 10 dealing with momentum. But the idea here is if the mass increases, then the moment of inertia also increases. Okay? And we're going to find here in a minute exactly what that relationship is. What this tells us is if mass increases, inertia increases. If mass decreases, inertia decreases. If radius increases, then it increases. If radius decreases, then the moment of inertia decreases. I can give you a pretty neat, oh, I don't have the other one in here. Oh, okay, I'll have to get it for next time. With this object right here, we can talk about its inertia because all of the wood particles are all spread out evenly. But what would you think would happen if I were to take those particles and spread them all out and condense them to a disk, a nice ring around the edge, okay? You'd have that same mass, but it'd all be kind of on the end, okay? And so we would have had the same mass, but the radius would have increased, okay? And how do you think that would affect the moment of inertia? It would go up. In fact, I can't believe I don't have it. I thought I had it in here. But anyway, I have a disk of the exact same radius and diameter and the exact same weight, but it's a ring, and it will spin a lot longer than this. Okay, it takes a little longer for it to get going, but it'll spin a lot farther. Once again, we'll talk about that in momentum. All right, do you all have your worksheet? I'm looking for the one that looks like. Keep going, keep going. Yeah, this one right here. You're at the spot. Looks like that. In fact, it looks like rotational dynamics and moment of inertia. This thing right here. Okay. Well, we're going to simplify this down. Before we start talking about an actual object with a lot of different mass, we're going to boil this down to something really basic. We're going to say we've got a pivot point, we've got a stick, some rotator stick, which is basically dirt, and we have an object stuck on the end of it that we're going to apply a force, and we're going to cause this thing to rotate. Okay? So we're going to apply a force right there at some distance r. Okay? And it's going to be, for simplicity's sake, we're going to say that it's at a 90-degree angle, so that therefore theta is equal to 90. And when we calculate the torque, which is Fr sine theta, what's the sine of 90 degrees? 1. So the torque is just going to be the force times the radius. When we apply a force at a radius, it causes a torque, which will cause, right now, this object, it's to the very end of the lever here, one. You might need, I'll ask you to stand up if you need to. Right now, is this moving at all? No. When I apply a force, okay, it's going to have angular velocity. So therefore, I'm going to cause angular acceleration. Okay? So it's not just that now it's spinning. Now it's not spinning. I apply a force. There's been angular acceleration. It's gone from like here to doing this. Which is the same thing as if it was going at a regular angular velocity and then going faster and faster. Only difference is we're starting at 0. Okay? So, when I do that, we also have talked about that there's going to be something called tangential acceleration, because this point has been accelerated in that direction. So, this point, I've applied a force on a mass, and I get a tangential acceleration. Newton's second law says this, that tangential acceleration is equal to the force divided by the mass. That's just Newton's second law. The law that we saw earlier, the formula which relates tangential acceleration to all that other stuff, was this formula right here. Tangential acceleration is equal to angular acceleration times the radius. Angular acceleration is how many angles it's cutting and how that velocity is changing. Okay? You write this down on your paper. All right? So we're going to do a little bit of manipulation here and get our formulas here. So first off, I've got tangential, those two things are equal. So I'll say alpha r equals F over m. Then divide both sides by the radius. Alpha equals F divided by the mass times the radius. All right? If I'm then, for no apparent reason, multiply this by r over r, I get alpha is equal to Fr over mr squared. Well, what is Fr? torque. So torque divided by mr squared. All right? And that is our $1 million formula for right now. Well, it's not, I guess, this is the $500,000.
For torque or tangential?
It's showing the relationship between the angular acceleration. What sort of angular acceleration are you going to get if you have a given torque, okay, so a force at a distance, of some mass at some radius, okay? You're like, what in the world is this good for? You're talking about one point rotating around something. When in the world are we going to deal with just one point rotating around something else? And you say, just whoa, hold on, all right? We never deal with just one point in physics. We normally deal with like an object, okay? And guess what that object is made up of? A whole bunch of points. So what we do is we just add those all up. We say this point plus this point plus this point, all going around. So this, I'm going to simplify it for the sake of argument to just 3, okay? I've got some sort of object. I've got a mass here, I have a mass here, and I have a mass here. They're all at different radii from the center of rotation. This thing is going to be spinning around. And they've all been given a force. This one has been pushed this way. This one's been pulled this way. This one has been pushed that way, okay? So what we can do is we can figure out, first off, the torque on each particle. So this particle has been given a torque, a force at a distance. So the torque on particle 1 is just what we say, the same, that previous formula that we saw a second ago. Let me go back. Oh, did it not save it? I guess it didn't save it. We had alpha equals torque divided by mr squared. So the next step, sorry about that, would be torque is equal to alpha times mr squared. That's the slight variation on that. So torque is equal to alpha times mass 1, radius 1 squared. The torque on point 2 is alpha mass 2 r2 squared. The torque on particle 3, alpha mass 3 radius 3 squared. So you got somebody pushing, somebody pulling, somebody pushing that, and all of those together are causing this thing to rotate. So we can say the net torque is, well, lucky for us, this one's positive, this one's positive. It's going to cause it to rotate in this direction. This one to make it rotate in this direction. This one will make sure it'll rotate in this direction. Okay? And so the net torque, we can just add them all up. So torque 1 plus torque 2 plus torque 3. So the net torque, I'll just substitute these values in here. M1 R1 squared alpha plus M2 R2 squared alpha plus M3 R3 squared alpha. That is equal to the net torque. That the torque is what's caused this thing to start spinning. If you notice, each one of those alphas, I can factor that out from each one of those, or even better yet, I'll divide by all of those. I could say divide everything by alpha, so I'd have the net torque divided by alpha is equal to M1 R1 squared plus M2 R2 squared plus M3 R3 squared. You see a pattern there? This mass times this distance squared, plus this mass times this distance from the pivot point squared, plus this mass times this distance, okay? I just picked 3 so you can see the pattern here. Or here the textbook, you can pick 3. What if you had 50 particles? You would just carry this on, right? M4, R4 squared, M50, R50 squared, okay? So you could go on and on and on, and you could just write, that's the summation, all right? Which means you just add them all up, of MI, RI squared. That means you just add all of those up. Okay? Now, we actually have a special name for this right here. And that is moment of inertia. Okay? If you add up all the masses at all their radiuses, then it equals moment of inertia. And if we look over here, that formula matches what we have discovered, okay? Notice this, the I is in the numerator, the M and the R are both in the numerator. If the mass goes up, what's going to happen to the moment of inertia? It goes up. If the mass goes down, moment of inertia goes down. Jesus, head up, attention goes up. Radius goes up, moment of inertia goes up. Radius goes down, moment of inertia goes down, okay? So this right here, this is I, is called the moment of inertia. It's a measure, it's an actual number which tells us how much it really doesn't want to rotate, okay? And what we have here, the formula, I is equal to net torque over A. We can do a little modification of that. And you get this, we had a second ago, we had I is equal to net torque over alpha. You can multiply both sides by alpha, divide both sides by I, and you get angular acceleration is equal to net torque divided by moment of inertia. This is a huge formula. This is an AP formula. This is Newton's second law for rotation, okay? Find that on your formula charts. On your formula chart, it's going to have this. It's going to have a vector symbol over it, and it's going to be a kind of a very, it's going to be cursive A, or it's going to be alpha, which is different. They're going to write it like this: the summation of the torque vectors divided by the moment of inertia, or what we've been seeing, which we all know, the net torque, and the summation just means add them all up. So the net torque as a vector divided by the moment of inertia. Now, doesn't that formula look kind of similar? What does it kind of look like? What about, yes, something for acceleration?
Linear.
The fourth equation. Yeah, that's got a special name. That's Newton's second law. Okay? This is Newton's second law for rotational motion. I don't have any posters for that, but if you'd like some extra points, you can show me an idea. I'd love to have a poster on that. Okay? In fact, right here in this, I got a little bit of space. I'll write over here. So here's angular acceleration. That means how fast it's changing in its rotational velocity is the net torque over the moment of inertia. That means, all right, so let's see if I can get this, if I can observe. All right, let's say you've got something spinning. That's not going to spin very well. All right, something spinning. Okay, and I apply a torque to it. It's spinning. I can hit it, then it's going to start spinning faster. The velocity has changed. There has been angular acceleration. Okay, how much angular acceleration has there been? Well, it depends on the torque that I put on it, and it depends on the moment of inertia, where the mass is located and how much mass there is. Okay, let me say that again. All right, if I apply a torque to something and it starts spinning, okay, the question is, what's going to, how fast is it going to change in its spin rate? That's angular acceleration. Well, it depends on whether I do this, a little small torque, or a large torque, right? So it depends on the torque. It also depends on what's called the moment of inertia, which is how many of these bricks are stacked on here. Okay, how much mass is on it, but also, not just that, but where the mass is. As we discovered earlier, if the mass is really close, then it'll be easier to spin. If the mass is kind of far away, then there will not be as much angular acceleration. Okay? In fact, that analogy works for just linear acceleration. How fast something accelerates, how fast something moves, depends on how much force I'm pushing on it and how much stuff there is packed inside that object, which is the mass. So what I want you to think about is that, okay, torque is like force. In fact, it's force, but it's rotational. Okay? Moment of inertia is like mass. It is the rotational equivalent to mass. In fact, that's most textbook, older physics textbooks won't even talk about mass. They'll actually talk about inertia. They'll say inertia, which is how much something doesn't want to move, and then moment of inertia, which is how much something doesn't want to move rotationally. Okay? So you can see the similarities there. And then acceleration, that just means how fast it's, changing velocity. Alpha is how fast it's changing its acceleration. Okay? We would modify this Newton's second law to say, I guess it was F net, the net force. We would say that the net force, or we would say the summation of forces is equal to all those masses times their accelerations. Okay? We could do the same thing over here, where we could say the net torque, or the summation of the torques, add up all the torques, is equal to moment of inertia times alpha. Okay? Other things that we saw. If you have room, you can just add on to the bottom there. When talking about linear motion, okay, what did it mean if the net force on an object was 0? It told us, yep, that the net acceleration was 0. What did that tell us? What was constant? Okay, it meant that velocity was constant. What does that mean? Constant velocity. Okay, uniform motion, of course.
No acceleration.
No acceleration, that's right. Show me with your hand, what would that mean, constant velocity?
Oh, it doesn't change the
Okay.
direction.
Or
Not.
is that not constant velocity?
It is.
Yeah, that's true.
Yeah. Okay.
Yeah, it's a-
Means velocity constants, which means either velocity is equal to 0 or it's equal to some other number. Okay? That situation, that sort of dialogue, we can also talk about something that is moving, something that is rotating. Okay? So if the net torque is equal to 0, then that means that, well, give me the quantity here. Well, what corresponds? Angular acceleration. The net angular acceleration is 0. What is the angular equivalent to velocity? Angular velocity. So that means angular velocity, I'll put omega, angular velocity is constant. Which, all right, now with your hand or with your arm, show me constant angular velocity. Or, see how it has, I have 1 revolution per second. 1 Mississippi, 2 Mississippi, 3 Mississippi. See what I'm saying? So it's constant. So either, that means that omega either equals 0 or omega equals some number. All right, let's see if we can wrap this up with the demonstration. Okay, if I apply all right, I'm going to apply a torque to this. Right now, 0 angular velocity. Net torque? 0. I apply a torque to it. Boom, what happened? What happened just at that moment?
Acceleration.
Angular acceleration, that's right. Why does it stop?
Inertia.
No.
Acceleration. Or not.
Because there's acceleration in the opposite direction. That is correct. What causes that? What causes angular acceleration? A torque. What's causing the torque that makes it slows down? Not the moment of inertia. Moment of inertia is just a measure of how much it doesn't want to move.
Along the pivot point?
That is correct. The friction on the pivot point. You don't even think about it, but that's what happens, is that there's friction in between this part and the axle. As smooth as they are, there's still friction there, okay? In fact, there's enough friction that it slows it down. It slows it down pretty quickly. That friction is causing a negative torque, and that negative torque is causing a negative angular acceleration, which causes it going from 0, all right? Now it's going 5 radians per second, 4 radians per second, 3 radians per second, 2 radians per second, 0 radians per second. And
Wait,
stops.
is it also drag?
Is there drag? Yes. It is like nothing compared to the friction though. Friction is everything. Good question. All right, so today we talked about Newton's second law all over again, but with rotational stuff. All right, moment of inertia depends on the position of the mass, where the mass is, and how much mass there is. All right, see you next time.